Hey guys, tonight we travel so far back in time that even the dinosaurs would call it ancient history. You stand on a version of Earth so violent, so blisteringly hot, and so completely unwelcoming that your modern brain almost refuses to process it. There are no forests swaying in the wind, no birds overhead, no fish beneath the waves, mostly because there are no real waves yet. The planet beneath your feet looks less like home and more like someone accidentally left a pizza stone inside a volcano for 4 billion years. Rivers of lava stretch across the horizon, glowing orange beneath a sky thick with choking ash and sulfur clouds. Every few minutes, another asteroid slams into the surface hard enough to make entire continents shudder. Honestly, you probably won't survive this. Not because of the lava specifically, although that certainly isn't helping, but because the air itself would casually cook your lungs like microwaved spinach. So, before you get comfortable, take a moment to like the video and subscribe, but only if you genuinely enjoy what I do here. And while you're settling in tonight, post your location and local time down below. It's always strangely comforting knowing where everyone is drifting off from while we wander through 4.5 billion years of planetary chaos together. Now, dim the lights, maybe turn on a fan for that soft background hum, and let's ease into tonight's journey together. You arrive on Earth roughly 4.5 billion years ago, back when the planet is less a world and more a cosmic construction site. The surface churns endlessly beneath you, glowing cracks splitting apart black volcanic plains. Mountains barely have time to form before they collapse into molten rivers again. The moon hangs enormous in the sky, far closer than today, looming like a giant pale neighbor that forgot boundaries existed. Some scientists believe the moon formed after a Mars-sized object smashed into the young Earth, spraying molten debris into orbit where it slowly gathered itself together, which, honestly, is the most dramatic birth story imaginable. Your planet gets hit once and suddenly acquires a permanent glowing roommate. The mainstream historical fact here is simple but astonishing. Earth forms about 4.54 billion years ago from dust and debris orbiting the young sun. Tiny particles collide, stick together, and gradually build larger and larger bodies until gravity shapes them into planets. It sounds peaceful when summarized in textbooks. In reality, it resembles celestial demolition derby night. The sky above you glows reddish-brown through thick volcanic haze. There is no breathable oxygen. Instead, the atmosphere swirls with carbon dioxide, methane, ammonia, and water vapor. Every breath would feel like inhaling a chemistry experiment that immediately regrets your participation. Lightning flashes constantly through the clouds, illuminating the jagged landscape in brief silver bursts. Thunder rolls endlessly across the empty world. And empty really is the right word. There are no trees, no insects, no distant animal calls, just volcanic rumbling and impacts from space. The silence between explosions feels enormous. Historians still argue whether Earth cooled relatively quickly after its formation or whether parts of the surface remained molten for much longer than once believed. New evidence from ancient zircon crystals suggests liquid water may have existed surprisingly early, maybe even within the planet's first few 100 million years, which is slightly comforting. Somewhere amid this fiery nightmare, tiny pockets of calm might already be appearing. You begin walking across hardened volcanic rock, though walking may not be the best survival strategy here. The ground trembles constantly beneath your feet. Giant fissures split open without warning, exposing glowing magma below. Entire regions bubble like soup left unattended on the stove. And hovering overhead is the terrifying reality of the late heavy bombardment a period when countless asteroids and comets smash into the inner planets. Imagine trying to decorate your apartment while bowling balls crash through the ceiling every 6 minutes. That is basically Earth's situation. One particularly massive impact lights up the horizon, brighter than sunrise. Debris blasts upward into the atmosphere before raining back down as molten rock. Some impacts vaporize entire oceans before oceans properly exist. Others reshape vast stretches of crust. Yet strangely, these collisions may also help deliver water and organic molecules to the young Earth. Cosmic destruction accidentally lays groundwork for future biology, which feels very on-brand for the universe. You pause beside a field of black volcanic glass, still warm beneath your feet. Steam hisses upward through cracks. Above you, the young moon creates enormous tides across scattered pools of water beginning to gather in low regions. Days are shorter now, perhaps only 6 hours long, meaning sunrise and sunset race by at absurd speed. Your sleep schedule would collapse instantly. Somewhere a prehistoric version of insomnia already thrives. A quirky fringe tidbit from this era involves the idea that early Earth may once have had rings like Saturn. Some researchers speculate leftover debris from massive impacts temporarily formed glowing rings around the planet before eventually crashing back down or helping shape the moon further. Imagine standing beneath a fiery ringed Earth while lava oceans boil below. Beautiful, yes, also deeply concerning. The sun itself looks slightly dimmer than today, even though the planet feels unimaginably hot. Scientists call this the faint young sun paradox. The early sun produced less energy, so Earth theoretically should have been frozen. Yet greenhouse gases trap immense heat in the atmosphere, preventing global ice from dominating the surface. The climate system is already complicated before life even arrives to make things weirder. As time slowly passes, the violence begins easing ever so slightly. The crust thickens. Some regions stabilize for longer periods. Water vapor condenses high above into dark storm clouds stretching from horizon to horizon. Rain begins falling. At first, it evaporates instantly against scorching rock. But eventually the planet cools enough for liquid water to remain. And then the rain truly starts. Not for a few hours, not for a weekend. Rain falls for thousands, perhaps millions of years. Endless black clouds release boiling torrents across the rocky world. Steam rises everywhere. Valleys fill, basins deepen. The first primitive oceans slowly gather beneath the storm-dark sky. You stand at the edge of one of these newborn seas as lightning flashes across its surface. The water looks dark green beneath the volcanic atmosphere. Waves crash against black basalt shores untouched by life. No footprints mark the sand because there is no sand yet. No shells, no driftwood, only raw stone and restless water beneath alien skies. Still, something profound has changed. Earth no longer looks like a molten wound in space. For the first time, it begins resembling a world. The rain keeps falling long after you stop trying to count the storms. Thick clouds churn endlessly overhead, dark as spilled ink, while newborn oceans spread wider across the cooling crust. Water rushes through volcanic valleys, carrying dissolved minerals into basins that deepen year after year. Steam curls upward from black shorelines where molten rock still glows beneath the surface. The entire planet smells faintly of sulfur, wet stone, and something metallic, like a factory kettle left boiling for several geological eras too long. You stand beside one of Earth's first stable coastlines and watch waves crash against jagged volcanic rock. It feels oddly peaceful compared to the asteroid apocalypse from earlier. Sure, the atmosphere could still quietly erase your lungs in seconds, and random lava eruptions remain very much on the menu. But the planet is beginning to settle into rhythms instead of tantrums. This is the Hadean drifting toward the Archean, an era where Earth slowly transforms from a hellish furnace into something capable of supporting life. And honestly, the fact that life eventually appears here at all feels like the universe showing off. The mainstream historical fact in this section is one scientist's love because it changes everything. Earth's oceans likely formed incredibly early, perhaps over 4 billion years ago. Water condensed from atmospheric vapor, while additional water may have arrived aboard icy comets and mineral-rich asteroids. Without these oceans, life as you know it never gets a chance to begin. You kneel beside a steaming tide pool. The water bubbles softly from geothermal heat below, rich with dissolved chemicals leaching from volcanic rock. Iron, carbon compounds, sulfur, phosphorus, all the ingredients for strange chemistry experiments swirl together in warm, shallow basins. Lightning cracks overhead, occasionally striking the water with explosive flashes. And somewhere amid this chemical soup, nature begins fumbling toward biology. No one knows exactly how life starts. Scientists still debate the details fiercely. Historians still argue whether life first emerged in shallow tidal pools, deep-sea hydrothermal vents, underground rock fractures, or perhaps multiple places at once. Every theory sounds slightly unbelievable. Somehow dead chemistry learns how to copy itself, and once that happens, the universe changes permanently. You wander along the coastline while massive storms roll overhead. Rainwater pours into primitive oceans, already tinted green from dissolved iron. The moon hangs enormous in the sky, closer than today, pulling gigantic tides across the young planet. Some coastlines flood and drain repeatedly within hours, creating wet-dry cycles that researchers think may help complex molecules form. It is essentially nature running endless chemistry trials without supervision, which, if you think about it, explains a lot about life. Far offshore, volcanic islands rise from the sea like smoking black teeth. Around them, hydrothermal vents pump mineral-rich water into the oceans. These vents are among the leading suspects in the mystery of life's origin. Hot water surges through cracks in the seafloor carrying metals and chemicals that could help simple molecules organize into more complex structures. Tiny mineral chambers within the vents may act like microscopic laboratories. Tiny laboratories that eventually produce trilobites, whales, raccoons, and people arguing online about pineapple pizza. You dip your hand into the warm seawater. No fish dart away. No algae drift beneath the surface. The oceans remain lifeless to the naked eye. Yet invisible chemistry quietly grows more ambitious with every passing millennium. A quirky fringe tidbit from this era involves the theory of panspermia. The idea that life's ingredients or even primitive microbes themselves may have arrived from space aboard meteorites. Some scientists treat it cautiously, while others openly explore the possibility. The theory does not explain how life originally begins, only that Earth may not have been the sole starting point. Which means the first ancestor of all living things could technically be an interplanetary hitchhiker. Quite the travel story, honestly. The atmosphere slowly changes too. Volcanic gases continue pouring skyward, thickening clouds that blanket much of the planet. Methane traps heat efficiently, keeping the oceans liquid beneath the faint young sun. Thunderstorms rage almost constantly. Lightning flashes so frequently that entire horizons flicker blue-white through the darkness. And yet, beneath all this violence, Earth becomes strangely beautiful. You watch dawn spread across the ocean, one short morning. Days are still far quicker than modern ones, perhaps lasting only 10 or 12 hours. The sun rises fast, glowing dim red through volcanic haze. Light reflects across endless dark water, while steam rises from distant shorelines. For the first time, the planet feels less like a wound and more like a beginning. Deep beneath the waves, chemistry inches closer towards something extraordinary. Simple organic molecules combine into amino acids and other building blocks. Fatty membranes form naturally in water, creating tiny bubbles capable of separating internal chemistry from the outside world. Some molecules begin copying themselves imperfectly. Mistakes occur. Variations emerge. That is evolution's opening move right there. Tiny mistakes accumulating over impossible spans of time. Historians still argue whether RNA came before DNA in early life. The RNA world hypothesis suggests self-replicating RNA molecules may have acted as both genetic material and chemical catalysts before DNA and proteins evolved later. In simpler terms, life might have started with molecular multitasking because early Earth apparently could not afford specialized employees yet. You continue walking through volcanic shallows where mineral deposits create strange layered formations. Some researchers believe clay surfaces help organize organic molecules into more complex arrangements. Others think ultraviolet radiation from the young sun plays a crucial role. Every answer opens three more questions. That uncertainty gives this era its eerie magic. Nothing here looks alive, yet everything is preparing for life. The wind strengthens as another storm approaches. Waves pound the coast harder now, carrying foam across black rocks polished smooth by relentless tides. Somewhere beneath these waters, perhaps near a hydrothermal vent glowing in the darkness, the first true living cells may already exist. Tiny, fragile, invisible, but alive. If you could peer into a microscope billions of years too early, you might see simple microorganisms floating through warm oceans, feeding on chemical energy instead of sunlight. No eyes, no mouths, no thoughts, just microscopic survivors dividing endlessly in the dark. Every oak tree, shark, dinosaur, and sleepy human listening tonight traces back to those humble beginnings. And the planet itself seems to sense the shift. The oceans no longer feel empty. They feel expectant. The oceans stretch endlessly beneath dark skies, their surfaces rolling beneath storms that never seem fully finished. Yet something has changed since you last stood on these shores. The water no longer feels empty in the same way. Hidden beneath the waves, life has arrived quietly, without fanfare, without orchestral music, without even a decent logo. No giant creature bursts dramatically from the sea. No heroic soundtrack swells. Instead, the rulers of Earth are microscopic cells drifting through warm, ancient oceans like tiny blobs with surprisingly strong survival instincts. And honestly, these little organisms are about to outperform almost every species that comes after them. You lean over a shallow coastal lagoon where strange layered structures rise from the water like lumpy stone pancakes. These are stromatolites, built by colonies of microbes trapping sediment grain by grain over immense spans of time. They do not look impressive. If someone showed you one in a parking lot, you might assume it was an unusually judgmental rock. Yet, these structures represent some of the earliest visible evidence of life on Earth. The mainstream historical fact here is enormous in importance. By at least 3.5 billion years ago, microbial life already thrives across Earth's oceans. Fossilized stromatolites found in places like Western Australia preserve traces of ancient bacterial communities that help reshape the planet itself. You crouch beside the shallow water as sunlight filters weakly through thick clouds overhead. Inside slimy microbial mats, billions upon billions of bacteria live layered together in dense colonies. Some feed on chemicals released from volcanic activity. Others begin using sunlight through photosynthesis, one of the most revolutionary biological inventions in Earth's history. At first, these microbes do not produce oxygen the way modern plants do. Early photosynthesis likely relies on different chemicals, including sulfur compounds. But eventually cyanobacteria appear, tiny blue-green organisms capable of splitting water molecules and releasing oxygen as waste. One of the most important substances for complex life begins as microscopic garbage. The oceans now teem with these tiny organisms, though teem feels generous because you still cannot see them without a microscope. No fish swim below. No seaweed sways in currents. Just microbial films coating rocks, drifting through shallow seas and quietly transforming the atmosphere molecule by molecule. Historians still argue whether life evolved only once or multiple times independently during these early eras. Some researchers suspect several primitive lineages may have appeared, with only one surviving ancestor eventually dominating all later life. Imagine entire forgotten branches of biology erased so completely that not even fossils remain. Evolution can be very rude that way. The coastline itself looks alien compared to modern beaches. The tides drag mineral-rich water across barren volcanic flats. Iron dissolved in the oceans gives the water strange greenish or reddish hues depending on local chemistry. The sky remains hazy with methane and volcanic gases, creating sunsets that glow deep orange through thick atmospheric fog. And the moon still appears much larger overhead. You wander across rocky shallows where stromatolites form broad colonies stretching toward the horizon. Some rise in layered domes. Others grow in branching ridges. They resemble strange coral reefs designed by sleepy bacteria with unlimited patience. A quirky fringe tidbit from this era involves theories that early microbes may have survived deep underground during devastating asteroid impacts, essentially hiding inside Earth's crust while the surface became temporarily sterilized. Scientists have found modern microbes living miles beneath the surface today, feeding on chemical reactions inside rocks, which means some ancient organisms may have basically spent Earth's worst disasters underground, avoiding responsibility. Not the worst survival strategy, honestly. The days continue lengthening very slowly as the moon drifts farther away over millions of years. Tides remain powerful, constantly stirring coastal environments where microbial colonies flourish. Lightning storms still roam the planet, though impacts from space happen less frequently now. Earth feels calmer, but only by prehistoric standards. A volcanic eruption large enough to terrify modern civilization barely qualifies as background scenery here. You kneel beside a warm tidal pool covered in slippery microbial mats. Tiny bubbles rise through the water. Oxygen. At first, the gas reacts immediately with dissolved iron and volcanic chemicals, never accumulating in the atmosphere. Vast amounts of iron precipitate onto the seafloor as rust-colored minerals, creating banded iron formations that future humans will eventually mine for steel. So yes, in a deeply indirect way, ancient bacteria help build skyscrapers billions of years later. The scale of time here becomes difficult to grasp. These microbial worlds dominate Earth for over 2 billion years. 2 billion. Dinosaurs, by comparison, barely get a brief guest appearance. Humanity does not even qualify as the trailer before the movie starts. And through all that time, life remains mostly microscopic. You walk beneath towering volcanic cliffs while shallow seas lap quietly below. The air smells sharp and mineral heavy. There is still no breathable oxygen for you, despite cyanobacteria producing increasing amounts underwater. The atmosphere contains methane, carbon dioxide, and nitrogen in far greater abundance. But change is coming. Slowly, relentlessly, cyanobacteria continue releasing oxygen into the oceans. At first, the oxygen disappears into chemical reactions. Iron rusts. Minerals oxidize. But eventually, those sinks begin filling up. Oxygen starts lingering longer in seawater. The microbes themselves do not realize they are preparing a planetary catastrophe. For many ancient organisms adapted to oxygen-free environments, oxygen is toxic, deadly, corrosive. Imagine waking up one morning to discover trees suddenly exhale bleach. That is roughly how alarming this development becomes for anaerobic life. Historians still argue exactly how rapidly oxygen levels rose during this transition. Some evidence suggests pulses and fluctuations rather than one sudden shift. Others believe localized oxygen oases may have formed in shallow seas long before atmospheric oxygen became widespread. Either way, Earth is approaching one of the greatest transformations in planetary history. You stand on a rocky coastline at dusk while microbial mats glisten beneath fading light. The sea rolls endlessly before you, calm on the surface yet revolutionary underneath. Tiny cyanobacteria continue their invisible labor beneath the waves, releasing oxygen, bubble by bubble, into a world utterly unprepared for it. The sky darkens overhead, and somewhere deep in the ancient oceans, the future quietly begins poisoning the past. The oxygen keeps coming. Not in dramatic gusts or swirling clouds you can actually watch spreading across the planet, but slowly, invisibly, molecule by molecule. Tiny cyanobacteria continue floating through the oceans beneath dim sunlight, tirelessly producing oxygen as a byproduct of photosynthesis. They have no idea they are reshaping Earth forever. They are microscopic organisms simply trying to survive, and yet their collective activity triggers one of the greatest environmental disasters in planetary history, which is both impressive and slightly concerning. You stand beside an ancient shoreline, nearly 2.4 billion years ago, as waves roll across rust-colored shallows. The oceans themselves are changing color now. Vast amounts of dissolved iron react with free oxygen, falling out of seawater and settling across the seafloor in layered deposits. These become the famous banded iron formations. Future humans will eventually carve into mountains, smelt into steel, and somehow transform into office buildings where people eat sad desk lunches under fluorescent lighting. Evolution has strange long-term planning. The mainstream historical fact here is known as the Great Oxygenation Event, sometimes called the Oxygen Catastrophe. Around 2.4 billion years ago, oxygen produced by cyanobacteria begins accumulating in Earth's atmosphere for the first time in significant amounts. This permanently alters the chemistry of the planet and wipes out countless anaerobic organisms unable to tolerate oxygen-rich conditions. For many early microbes, oxygen is essentially poison gas. You walk across black volcanic rock while reddish waves lap against the shore. The sky above still looks hazy and strange, though methane levels begin dropping as oxygen reacts with atmospheric gases. This weakens the greenhouse effect that once kept Earth warm beneath the faint young sun. And then things get cold, very cold. Some scientists believe rising oxygen contributes to massive global glaciations during this era. Ice sheets spread across continents. Temperatures plunge. Entire oceans may partially freeze over. Earth swings from steaming volcanic greenhouse into a frozen world with breathtaking speed on geological timescales. Historians still argue whether these early glaciations covered the entire planet or left large areas of open water near the equator. evidence remains fiercely debated. Some researchers imagine nearly complete global ice cover, while others argue for a slushier Earth with surviving refugees for life. Either way, the climate turns hostile enough to make modern winter complaints sound adorable. You continue across a frozen coastline where glaciers grind slowly toward the sea. Icebergs drift beneath dark skies tinged faintly orange through volcanic haze. The silence feels enormous here. Life survives mostly in microbial communities beneath ice, near hydrothermal vents, or in isolated pockets of liquid water. And through it all, oxygen keeps building. One bizarre consequence of oxygen accumulation is the eventual formation of the ozone layer high in the atmosphere. Ozone absorbs harmful ultraviolet radiation from the sun, making Earth's surface safer for future life. Before this protective shield forms, ultraviolet light blasts the planet relentlessly. Stepping outside without protection would be less beach day and more surface of Mercury speedrun. A quirky fringe tidbit from this period involves strange rock formations called dropstones. Large rocks embedded inside ancient sediments where they clearly do not belong. Scientists interpret them as evidence of glaciers and floating icebergs dropping debris into oceans billions of years ago, which means even Earth's oldest frozen worlds still manage to leave behind geological clutter. You pause beside towering cliffs striped with iron-rich layers: red, black, silver. Layer after layer marks cycles of oxygen production and chemical change over unimaginable spans of time. These rocks become a planetary diary, written long before animals exist. The atmosphere slowly transforms from methane-heavy haze into something clearer. The sky itself may begin appearing bluer as oxygen increases, though it still lacks modern levels. Sunlight filters across frozen seas while volcanic eruptions continue puncturing the horizon with fiery glow. And somewhere beneath the ice, life adapts. Some microbes retreat into oxygen-free environments. Others evolve ways to tolerate or even exploit oxygen chemically. Eventually, certain cells learn to use oxygen for respiration, unlocking far more efficient energy production. This innovation becomes the foundation for complex multicellular life billions of years later. Basically, oxygen starts as a toxic disaster before becoming biological rocket fuel. You walk through shallow coastal waters where microbial mats still dominate the world. Stromatolites rise in strange layered domes beside icy shorelines. No fish disturb the water. No birds fly overhead. Yet Earth feels alive in a deeper way now, transformed from a raw chemical world into a biosphere actively reshaping its own environment. Historians still argue whether oxygenation occurred in pulses rather than one steady rise. Some evidence suggests atmospheric oxygen may have surged, collapsed, and risen again multiple times before stabilizing. Earth's early climate and chemistry remain incredibly complicated, almost frustratingly so. Every ancient rock seems to whisper, "Good luck figuring this out." You glance upward as auroras shimmer faintly across the darkening sky. Earth's magnetic field already shields the atmosphere from solar radiation, helping preserve the conditions necessary for life. Without that invisible magnetic protection, solar winds might strip away much of the atmosphere over time. So somewhere beneath your feet, Earth's molten core quietly keeps the entire planet habitable while receiving absolutely no appreciation. Classic support role energy. As millions of years drift by, oxygen slowly spreads farther through the oceans and atmosphere. The world remains mostly microbial, but the stage is being prepared for greater complexity. Cells capable of using oxygen gain evolutionary advantages. New ecological relationships emerge. Tiny organisms engage in microscopic warfare, cooperation, and survival strategies that future biology textbooks will desperately try simplifying. The frozen landscapes eventually retreat somewhat. Volcanoes pump carbon dioxide back into the atmosphere. Glaciers melt. Oceans expand again beneath clearer skies. You stand at sunset beside an ancient sea now streaked with red mineral deposits. Cyanobacteria continue releasing oxygen beneath the waves, their invisible work reshaping continents, climates, and futures not yet imaginable. The planet breathes differently now, and for the first time in Earth's history, the atmosphere begins preparing for animals that do not yet exist. The cold settles into everything. Not the kind of winter chill that makes you reach for a blanket and dramatically complain online about your frozen toes. This is planetary cold. Ancient, crushing, world-spanning cold. Ice stretches from horizon to horizon beneath dim sunlight, reflecting pale blue across a silent Earth. Glaciers tower like frozen mountain ranges. Oceans disappear beneath kilometers of ice. Even near the equator, the planet glitters white beneath thick cloud cover. You stand in the middle of snowball Earth. And honestly, this place feels less like prehistoric Earth and more like a forgotten moon drifting too far from its star. The mainstream historical fact here is extraordinary. During parts of the Cryogenian period, roughly 720 to 635 million years ago, Earth experienced severe global glaciations that may have covered nearly the entire planet in ice. Geological evidence from tropical regions suggests glaciers once reached astonishingly low latitudes, implying a frozen world unlike anything humans have ever witnessed. The wind howls across the ice plains around you. Snow drifts endlessly beneath grey skies while distant volcanoes puncture the horizon with faint red glow. Beneath your feet, the ocean still exists far below the ice shell, dark and hidden beneath kilometers of frozen crust. Life survives down there somehow, tucked into isolated refuges beneath the frozen surface, which is comforting in a very tiny, microbial sort of way. You trudge slowly across the frozen landscape while ice creaks beneath unimaginable pressure. The air bites sharply now, though oxygen levels remain lower than modern Earth. Glaciers grind across ancient continents, scraping rocks and carving valleys that future geologists will stare at with delighted confusion. Historians still argue whether snowball Earth truly froze the entire planet or whether thin belts of open ocean remained near the equator. Some scientists support a slushball Earth model instead, where patches of dark seawater survive between massive ice sheets. Either possibility sounds deeply inconvenient for anything hoping to enjoy a casual swim. Above you, the sun appears faint through dense cloud cover. Ice reflects huge amounts of sunlight back into space, cooling the planet even further. This creates a runaway feedback loop. More ice causes more cooling, which creates even more ice. Earth basically forgets how to stop freezing. You continue onward through an endless white wilderness broken only by volcanic ridges. Beneath the ice, however, the planet remains active. Volcanoes continue erupting. Hydrothermal vents still release heat and minerals into the oceans. Tectonic plates grind slowly onward beneath frozen continents. Earth's interior never sleeps, even when the surface resembles a giant cosmic freezer. A quirky fringe tidbit from this era involves the possibility that giant glaciers grinding across rocks may help release nutrients into the oceans once melting begins later on. Some researchers think these nutrients contribute to evolutionary explosions afterward, meaning Earth's worst ice age might accidentally fertilize the future. Nature really does enjoy dramatic resets. You pause beside a cliff of ancient blue ice stretching high overhead. Tiny particles of volcanic ash darken some layers. Others glow faintly turquoise beneath scattered sunlight. The silence feels overwhelming here, broken only by distant cracking sounds echoing across the frozen plains. Yet life survives. Deep beneath the ice, microbial ecosystems cling to existence near hydrothermal vents and isolated liquid pockets. Tiny organisms feed on chemical energy rising from Earth's interior. Some may live beneath translucent ice, where dim sunlight still penetrates enough for photosynthesis. These microscopic survivors endure conditions that seem impossible from the frozen surface above. Honestly, microbes deserve far more respect than they usually get. As millions of years pass, volcanoes continue releasing carbon dioxide into the atmosphere. Normally, weathering processes would remove much of this gas, but with continents buried beneath ice, weathering slows dramatically. Carbon dioxide accumulates over immense spans of time, gradually strengthening the greenhouse effect again. The planet begins warming, slowly at first, almost imperceptibly. Then the ice starts retreating. You watch meltwater carve channels through glaciers the size of continents. Icebergs break apart and crash into dark oceans, re-emerging beneath brighter skies. The transition must look astonishing from orbit. A frozen white sphere, gradually revealing blue oceans and rocky land once more. And when the thaw finally arrives, it arrives hard. Some scientists believe snowball Earth ends in catastrophic greenhouse conditions. Carbon dioxide concentrations may have become extremely high after millions of years trapped beneath frozen conditions. Once melting begins, temperatures rise rapidly. Torrential rains lash freshly exposed continents. Rivers pour minerals into the oceans. Earth swings violently from deep freeze to humid greenhouse. The climate system remains wonderfully terrifying. Historians still argue exactly how these glaciations influence later evolution. Many researchers suspect the environmental stress helps drive biological innovation afterward. Harsh conditions eliminate weaker ecosystems, while isolated populations adapt in new ways. Once conditions improve, life diversifies dramatically. You stand now beside an icy shoreline where meltwater streams rush toward dark, open seas. The sky looks clearer than in earlier ages. Oxygen levels have increased significantly since the cyanobacterial revolutions billions of years earlier. The ozone layer shields the surface more effectively now. Earth feels less alien than before, though still profoundly empty compared to modern times. No forests line the coasts, no animals roam the land. But change approaches quietly beneath the waves. In the recovering oceans, more complex cells called eukaryotes already exist. Unlike simpler bacteria, these cells contain internal structures, including nuclei and energy-producing mitochondria. Some scientists think mitochondria originate when one cell swallows another ancient microbe and, instead of digesting it, forms a partnership. Which means every complex cell alive today is technically built on one of history's strangest roommate agreements. You walk along the thawing coast while strange microbial communities spread across wet rocks exposed by retreating ice. Nutrients flood into the oceans from freshly weathered land. Conditions stabilize gradually. And somewhere in these recovering seas, multicellular life begins experimenting with new forms. The frozen world is ending. Something softer, stranger, and far more complicated waits beyond the ice. The ice retreats farther every century, exposing dark coastlines that have not seen open air for millions of years. Meltwater rivers roar across bare stone, carrying minerals into widening seas beneath calmer skies. Earth feels quieter now, less violently unstable than the inferno of its youth or the frozen grip of snowball Earth. Oxygen drifts through the atmosphere in steadily increasing amounts. The oceans shimmer beneath soft sunlight, and for the first time, life begins trying out larger bodies. Not giant monsters yet, nothing with claws or fangs or dramatic cinematic entrances. Instead, the seas fill with strange soft organisms that seem almost experimental, as if evolution is doodling ideas before committing to final designs. You wade through shallow coastal waters of the Ediacaran period, roughly 635 to 541 million years ago. Beneath the surface, peculiar shapes cover the seafloor like living quilts. Some resemble fern fronds swaying gently in currents. Others look like ribbed discs, flattened ovals, or wrinkled tubes pressed into mud. Many have no mouths, no eyes, no obvious limbs, and absolutely no interest in helping future scientists classify them neatly. Honestly, they look like biology half asleep. The mainstream historical fact here is that the Ediacaran period contains some of the earliest large multicellular organisms ever discovered. Fossils from places like Australia, Canada, and Namibia reveal bizarre soft-bodied life forms unlike most modern animals, representing a major step toward complex ecosystems. You drift above the ancient seabed while pale organisms ripple gently beneath the current. Some anchor themselves to the sediment like soft sea plants, though many are probably animals. Others glide slowly across microbial mats covering the ocean floor. The water remains relatively shallow and oxygen-rich compared to earlier eras, creating conditions that allow larger bodies to evolve. Historians still argue whether many Ediacaran organisms are direct ancestors of modern animals or strange evolutionary side branches that eventually disappear entirely. Some researchers think certain species resemble early jellyfish, worms, or sea pens. Others argue they belong to completely extinct biological experiments with no living descendants, which is both fascinating and slightly tragic. Imagine surviving hundreds of millions of years only to become an evolutionary footnote shaped vaguely like a wet leaf. You continue through warm coastal shallows where microbial mats still blanket much of the seabed. These mats help preserve fossils by trapping sediment around soft bodies after death. Without them, many Ediacaran organisms might vanish from history entirely because soft tissue normally decays far too quickly to fossilize well. The atmosphere feels gentler now. The sky appears bluer than during Earth's earlier methane-heavy ages. Sunlight penetrates the water more clearly. Tides rise and fall across broad continental shelves teeming with these strange communities. A quirky fringe tidbit from this era involves a fossil called Dickinsonia, one of the most famous Ediacaran organisms. Scientists debated for decades whether it was a fungus, a lichen, an animal, or something else entirely. Some even joked it resembled an inflatable bath mat. More recent chemical evidence suggests it likely belongs to the animal kingdom, though its exact lifestyle remains mysterious. Ancient Earth apparently specializes in producing organisms that confuse everybody equally. You kneel beside the shoreline while waves wash over soft sediment dotted with impressions from these peculiar creatures. Some leave faint movement trails behind them. Others remain rooted in place, filtering nutrients from seawater. Predation still appears limited here. Most organisms lack shells, armor, or obvious defensive structures. It is a strangely peaceful world. No roaring predators yet, no jaws snapping shut. Just quiet drifting life spread across shallow seas beneath soft light. But that peace may not last much longer. Historians still argue whether rising oxygen levels directly trigger the appearance of larger multicellular organisms during this era. Some researchers believe oxygen reaches a crucial threshold, allowing bigger, more energy-demanding bodies to evolve. Others think genetic innovations matter more than environmental conditions alone. Either way, complexity accelerates. You walk along a tidal flat where strange disc-shaped organisms lie, half buried in wet sediment. The continents themselves look unfamiliar now. Smaller landmasses drift across the globe rather than one unified supercontinent. Volcanic activity continues shaping coastlines, though Earth feels far more stable than during its violent youth. Storms still sweep across the seas, but now waves crash onto shores inhabited by living communities instead of barren stone. And beneath the surface, evolution grows more ambitious. Some organisms begin burrowing into sediment, disturbing ancient microbial mats that once covered vast seafloor regions undisturbed. This seemingly simple behavior changes marine ecosystems dramatically. Burrowing introduces oxygen deeper into sediments and reshapes habitats for countless smaller organisms. Tiny worms basically invent underwater landscaping. You pause beside a shallow lagoon, glowing gold beneath sunset. Soft-bodied creatures drift gently in the current, while microbial films shimmer across submerged rocks. The water smells mineral-rich, but cleaner somehow than the sulfurous seas of earlier Earth. The world feels alive now in a visible way. And yet, something strange lingers over the Ediacaran oceans. Many organisms seem almost temporary, as though evolution is testing possibilities without fully committing to them. Some body plans appear nowhere again in later life. Others may represent the earliest versions of future animal groups. This uncertainty gives the era its haunting quality. You are witnessing Earth before recognizable animals dominate, before eyes become common, before skeletons spread, before teeth, claws, and proper prehistoric chaos arrive. A few early predators may already exist, but ecosystems remain relatively gentle compared to what comes next. The ocean floor is soft, quiet, and alienly calm. Then subtle changes begin appearing. Tiny mineralized shells emerge among microscopic organisms. Burrows grow more complex. Movement patterns become more active. Evolution inches toward an explosion of diversity, waiting just beyond the horizon. The strange, quilted world of the Ediacaran is nearing its end. Soon the oceans will fill with creatures so bizarre, armored, and energetic that even these soft-bodied pioneers will seem sleepy by comparison. And Earth itself is about to get wonderfully weird. The oceans lose their quietness first. For millions of years, the seafloor has been a slow-moving world of soft bodies drifting through calm water beneath gentle currents. But now something changes. Life accelerates. Predators emerge. Shells harden. Eyes evolve. Creatures begin chasing, biting, burrowing, and generally making the oceans a far more stressful place to exist. Welcome to the Cambrian period, roughly 541 million years ago, where evolution suddenly behaves like it drank 3 cups of prehistoric espresso. You descend beneath warm, shallow seas crowded with living forms unlike anything Earth has seen before. Trilobites scuttle across the sediment in enormous numbers, their segmented shells glinting beneath filtered sunlight. Worm-like hunters burrow through mud, searching for prey. Strange, swimming creatures dart overhead with flapping fins and grasping appendages. Everywhere you look, life experiments wildly with shape, movement, armor, and survival strategies. The mainstream historical fact here is one of the most famous events in paleontology, the Cambrian explosion. During this relatively brief geological interval, most major animal body plans appear in the fossil record. Complex ecosystems diversify rapidly, producing many ancestors of modern animal groups, and some creatures that look like they escaped from a fever dream. You float through the ancient sea while bizarre organisms crowd every level of the water column. One creature resembling a spiny vacuum cleaner glides past. Another looks suspiciously like a shrimp designed by abstract artists. Then comes Anomalocaris, among the top predators of the Cambrian oceans, swimming with flapping side lobes and grasping spiny appendages near its mouth. For years, paleontologists accidentally reconstructed it backward because its body parts were discovered separately. One fossil was mistaken for a jellyfish, another for a shrimp, another for a sea cucumber. Ancient Earth apparently enjoys practical jokes. Historians still argue whether the Cambrian explosion truly represents rapid evolution or whether earlier, soft-bodied ancestors simply fossilized poorly. Some scientists think complex animals evolved gradually during the Ediacaran, but only became more visible once hard shells and skeletons appeared. Others support a more sudden burst of diversification, driven by environmental and genetic changes. Either way, the oceans now feel crowded, energetic, and slightly dangerous. You drift past reefs built not by modern corals, but by sponge-like archaeocyathids. Trilobites swarm across the seafloor in massive numbers, some no larger than your fingernail, others surprisingly sizable. Their compound eyes are among the earliest advanced visual systems ever evolved. Suddenly, organisms can see predators approaching, which unfortunately means predators also become much better at finding lunch. A quirky fringe tidbit from this era involves hallucigenia, one of the strangest Cambrian animals ever discovered. Early reconstructions literally placed it upside down, with tentacles walking on its back and spikes dangling uselessly below. Scientists later realized they had completely misunderstood the fossil. Even now, it still looks like a tiny nightmare cactus wandering the seafloor. You continue through the warm Cambrian Sea while schools of primitive swimming organisms dart overhead. Burrows crisscross the sediment beneath you. Ecosystems now contain predators, scavengers, filter feeders, grazers, and active swimmers, all interacting in increasingly complex food webs. Life has discovered competition, and competition changes everything. Skeletons and shells become evolutionary advantages because getting eaten is suddenly a very real concern. Calcium carbonate and other minerals strengthen bodies against predators. Claws, spikes, and armor spread rapidly. Natural selection intensifies as survival depends not just on enduring harsh environments, but on avoiding other hungry organisms. Honestly, evolution just invented the world's oldest arms race. You swim deeper where sunlight dims into blue-green darkness. Strange worm-like predators emerge from burrows with circular tooth-lined mouths. Tiny brachiopods cling to rocks, filtering particles from the water. Jellyfish pulse slowly through the currents above. The oceans smell different now too, richer somehow, more biologically active. Decaying organic matter drifts through the water while microbial communities recycle nutrients beneath the sediment. Earth's biosphere has become vastly more interconnected than during earlier ages. Historians still argue whether rising oxygen levels play the decisive role in enabling larger, more active animals during the Cambrian. Higher oxygen may support greater energy demands for movement, predation, and complex nervous systems. Others point toward developmental genetic innovations, particularly genes controlling body organization. Tiny genetic tweaks, massive evolutionary consequences. You surface briefly near a rocky coastline, barren of visible life. The land remains mostly empty. No forests cover the continents yet. No animals crawl ashore. Winds sweep across bare stone, beneath skies far clearer than the ancient methane haze of earlier Earth. All the real action remains underwater. The continents themselves drift slowly across the globe, surrounded by shallow continental seas ideal for marine ecosystems. Volcanic islands dot the horizon, while tides surge across broad coastlines rich in nutrients. You pause beside the carcass of a trilobite half buried in sediment. Scavengers already swarm around it. Death now fuels entire ecosystems. Predation creates pressure. Pressure drives adaptation. Adaptation fuels diversification. The pace of evolutionary change feels astonishing compared to the slow microbial ages that came before. And yet, the Cambrian oceans remain profoundly alien. No fish with jaws yet patrol these waters. No sharks. No marine reptiles. Most creatures bear body plans unlike modern animals or combine familiar features in bizarre ways. The world still feels experimental, like Earth is trying every possible design just to see what works. A massive Anomalocaris glides overhead again, its large compound eyes scanning the seabed below. For Cambrian organisms, this creature is terrifying. For you, it resembles an aggressive shrimp wearing armor assembled by a distracted engineer. Perspective really matters in paleontology. As dusk filters dimly through shallow seas, trilobites continue crawling across the ocean floor in endless numbers. Strange armored worms burrow beneath microbial mats while soft-bodied swimmers drift through currents above. The calm, Ediacaran world has vanished completely now. Earth has entered the age of animals, and life will never slow down again. The continents sit empty beneath the wind. After the frenzy of Cambrian seas, the land feels almost unsettling in its silence. Waves crash against rocky shores. Rivers cut through barren valleys. Rain falls across stone plains untouched by roots or grass. No birds circle overhead. No insects buzz through the air. If you stand still long enough, you hear only water, wind, and the occasional volcanic rumble, far in the distance. Earth's oceans may already teem with strange animals, but the continents still resemble unfinished scenery, at least for now. You walk inland across damp stone during the Ordovician and Silurian periods, roughly 485 to 419 million years ago. Thin films of moisture cling to the ground near streams and tidal flats. Tiny green patches spread cautiously across wet rock surfaces. These are among the first pioneers of land. Simple moss-like plants and microbial communities inching outward from the water's edge. And honestly, colonizing land at this point takes absurd courage for something without bones. The mainstream historical fact here is that plants begin moving onto land during this era, gradually transforming barren continents into living landscapes. Early non-vascular plants resembling mosses appear first, followed later by primitive vascular plants capable of transporting water internally through specialized tissues. The change seems small at first. A few damp green mats hugging stream banks, tiny branching stalks no taller than your ankle. But these humble pioneers are about to alter Earth more profoundly than almost anything since oxygen itself. You kneel beside a patch of primitive vegetation growing along muddy ground. The plants lack flowers, seeds, or leaves as you know them. Many reproduce through spores, releasing microscopic particles into the air much like modern mosses and ferns. Their stems rise only a few centimeters high, yet even this modest growth stabilizes soil and begins pulling carbon dioxide from the atmosphere. Slowly, the continents start turning green. Historians still argue whether plants evolved on land once or through several separate transitions from aquatic ancestors. Some evidence suggests fungi may partner with early plants almost immediately, forming symbiotic relationships that help extract nutrients from rock and soil. Which means fungi are once again quietly involved in every major ecosystem breakthrough while getting almost none of the publicity. You continue inland where streams carve through rocky terrain, now coated with thin layers of dark soil. Before plants, rain simply washes minerals directly off bare stone. But roots, even primitive ones, begin trapping sediment and breaking rock apart chemically. The land itself starts changing shape, and with plants come opportunities. Tiny arthropods begin creeping onto shorelines. Early millipede-like creatures scuttle through damp environments, feeding on decaying organic material. Primitive arachnids explore muddy flats near water. They remain small and vulnerable, tied closely to moist habitats where they avoid drying out beneath the sun. Still, the invasion of land has begun. A quirky fringe tidbit from this era involves giant fungal structures called prototaxites. These towering organisms may grow over 20 feet tall, making them some of the largest land organisms of their time. Scientists debated for years whether they were giant fungi, algae, lichens, or something entirely different. Imagine wandering through an ancient landscape dominated not by trees, but by colossal mushroom towers. Earth really experimented with aesthetics before settling on forests. You pass one of these towering structures rising above low vegetation, like a dark pillar against the horizon. Around its base, tiny arthropods crawl through damp soil while primitive plants cluster beside shallow streams. The air smells different now too. Fresher somehow. Plants absorb carbon dioxide and release oxygen, slowly reshaping atmospheric chemistry over millions of years. The ozone layer thickens further, protecting land surfaces from ultraviolet radiation and making terrestrial environments increasingly hospitable. The skies themselves appear clearer than in Earth's ancient volcanic eras. Meanwhile, the oceans remain busy with evolutionary innovation. Jawless fish glide through shallow seas while coral reefs expand across warm tropical waters. Eurypterids, sometimes called sea scorpions, patrol coastal environments as formidable predators. Some species grow alarmingly large. One swims past offshore now, paddling through murky water with unsettling confidence. You know those moments when nature accidentally invents something that looks far too aware of your existence? This is one of them. Historians still argue how quickly atmospheric oxygen rises due to expanding plant life. Some researchers believe increasing oxygen contributes to later gigantism among insects and arthropods. Others think additional environmental factors matter more. Either way, the continents continue changing rapidly. You walk farther inland where low vascular plants now spread across floodplains in dense patches. Unlike earlier moss-like species, these plants contain specialized tissues that transport water upward, allowing taller growth. Some branch repeatedly into forked stems tipped with spore-producing structures. No flowers yet, no trees, but the foundations of forests already exist. Rain falls softly across the landscape while rivers meander between broad plains covered in primitive greenery. Soil deepens gradually as dead plant material accumulates and decomposes. Nutrient cycles grow more complex. Habitats diversify. The land no longer feels empty. Tiny arthropods scurry beneath damp vegetation. Primitive ecosystems spread along coastlines and riverbanks. Fungal networks thread invisibly through the soil. Earth's surface becomes biologically interconnected in entirely new ways. And the visual transformation is astonishing. For billions of years, continents remain mostly barren rock. Then slowly, over immense spans of time, life paints them green. You climb a low ridge overlooking an ancient floodplain at sunset. Below you, dark green patches stretch beside winding rivers beneath orange skies. The wind carries the earthy smell of wet soil and plant matter, scents impossible during Earth's earlier barren ages. Somewhere out there, evolution is preparing its next leap. Because once plants establish themselves properly on land, animals will follow more aggressively, and soon the skies themselves will hum with wings. The air feels heavier now, Not unpleasant exactly, just thick with oxygen and humidity beneath the dense canopy of Earth's first great forests. Warm mist clings to giant tree trunks while vast swamps stretch toward the horizon under dim filtered sunlight. Everywhere you look, green life towers upward in tangled abundance. Primitive forests cover enormous regions of the Carboniferous world, roughly 359 to 299 million years ago, transforming the continents into humid jungles unlike anything alive today. And hidden among the trees are insects the size of birds. So that is something you unfortunately have to process. You step carefully through shallow swamp water while giant club mosses rise over 100 feet above you. Their bark looks scaly and strange, more like enormous vertical reeds than modern trees. Horsetails as thick as telephone poles cluster beside slow-moving rivers. Ferns spread massive fronds across the damp forest floor. The mainstream historical fact here is that the Carboniferous period sees the expansion of vast swamp forests and extremely high atmospheric oxygen levels, possibly reaching over 30% compared to today's 21%. These conditions help fuel enormous arthropods and extensive coal-forming wetlands. Every breath feels rich and almost dizzying. Dead plant material accumulates in oxygen-poor swamp waters faster than it can fully decay. Over millions of years, buried layers of this vegetation compress into coal deposits humans will someday mine during the Industrial Revolution. Entire future civilizations will literally burn ancient forests to power trains, factories, and arguments about energy policy. The past always finds ways to haunt the future. You push through dense undergrowth while dragonflies with wingspans over 2 feet glide overhead. One lands nearby on a thick fern stem, its enormous compound eyes reflecting greenish light. This is Meganura, among the largest flying insects ever known. And yes, if one flew directly at your face right now, you would absolutely panic, regardless of how scientifically fascinating it is. Historians still argue exactly why arthropods grow so large during this period. High oxygen levels likely play a major role because insects breathe through passive air tubes rather than lungs. More oxygen allows larger bodies to function efficiently. Some researchers also point toward the relative absence of flying vertebrate predators at this stage. Basically, giant bugs evolve because nothing yet exists to tell them absolutely not. You continue deeper into the swamp forest where amphibians lurk beside murky pools. These early tetrapods descend from lobe-finned fish ancestors that gradually adapt to life on land. Some resemble oversized salamanders with broad heads and sprawling limbs. Others retain distinctly fish-like features despite spending increasing time ashore. Their movements still look awkward. Evolution has invented walking, but it definitely needs more practice. A quirky fringe tidbit from this era involves fossilized raindrop impressions found in ancient sediments. Scientists sometimes use these tiny marks to estimate atmospheric density in prehistoric times. Imagine reconstructing entire ancient climates from preserved rain splashes. Geology truly rewards people willing to become detectives for rocks. Thunder rumbles overhead while warm rain begins falling through the canopy. The forest erupts with sound now, insects buzzing, amphibians splashing through water, leaves rustling in humid wind. Compared to earlier eras, Earth suddenly feels noisy and alive. And the smell, rich mud, wet vegetation, rotting plant matter, fresh water. The forests breathe around you. You wade through a shallow marsh where giant millipedes called Arthropleura crawl slowly across decaying logs. Some reach lengths over 6 feet. Thankfully, they likely feed on plant material rather than chasing terrified mammals through the undergrowth. Still, encountering one unexpectedly at night would shorten your lifespan emotionally. Historians still argue where the frequent wildfires become more common due to elevated oxygen levels. Fossil charcoal suggests fires indeed spread through some carboniferous forests. Higher oxygen makes vegetation burn more easily, even when damp. So alongside giant insects and swamp forests, prehistoric Earth occasionally adds flamethrowers to the ecosystem. The continents themselves continue drifting together slowly. Vast tropical wetlands spread across equatorial regions while glaciers form near the southern pole. Climate patterns fluctuate over millions of years, but warm, humid forests dominate enormous areas. You climb over tangled roots beside a sluggish blackwater river. Schools of fish dart beneath the surface, while primitive sharks patrol deeper channels. Early reptiles begin appearing too, one of the most important evolutionary developments of the era. Unlike amphibians, reptiles evolve eggs with protective membranes that allow reproduction away from water. This innovation frees vertebrates from dependence on swampy breeding grounds. It is difficult to overstate how important this becomes. The egg basically unlocks the continents. You pause beside a fallen tree trunk covered in giant insects. Nearby, a small reptile-like creature scurries through leaf litter with surprising speed. Compared to the sprawling amphibians, it looks more agile, more independent somehow. A hint of future dominance. The skies darken toward evening while warm mist rises from the swamp. Dragonflies continue circling overhead beneath towering club moss forests, swaying gently in humid wind. Coal swamps stretch endlessly beyond the horizon, storing sunlight captured by plants in buried layers. Future humans will someday ignite. Earth feels lush now, complicated, fully alive. Yet this paradise remains unstable beneath the surface. Climate shifts are coming. The swamps will eventually shrink. Forests will collapse in some regions. And the great supercontinent Pangaea is slowly assembling, reshaping ecosystems across the planet. You stand beneath giant fern fronds while distant thunder rolls through the ancient forest. Amphibians croak from hidden pools. Massive insects hum through oxygen-rich air. For the first time, truly complex terrestrial ecosystems surround you on all sides. And somewhere among the tangled roots and dark waters, the age of reptiles quietly begins. Swamps begin drying at the edges first. Rivers shift course. Wetlands shrink. Seasonal droughts grow harsher across regions once buried beneath endless humid forests. The great carboniferous jungles still stand in many places, but Earth is changing again. Continents grind slowly together into a massive supercontinent called Pangaea, reshaping oceans, climates, and ecosystems on a planetary scale. You walk across a broad floodplain during the late Carboniferous into the early Permian, roughly 320 to 280 million years ago. The air feels warmer and drier now. Forests thin into open woodlands in some regions, while deserts spread across the growing continental interior. The world smells less like endless swamp water and more like hot soil, resin, and dust carried on dry winds. And out here, something remarkable is happening. Animals are finally learning how to live fully away from water. The mainstream historical fact here is that early tetrapods diversified dramatically during this era. Amphibians continue thriving in wetlands, but reptiles evolve key adaptations, especially the amniotic egg, allowing them to reproduce in dry environments far from lakes and rivers. It is one of evolution's greatest upgrades. You crouch beside a muddy riverbank where large amphibians lounge half-submerged in shallow water. Their bodies remain broad and sprawling, skin moist and vulnerable to drying out beneath the sun. Nearby, however, smaller reptilian creatures dart confidently across dry ground with tougher skin and more efficient movement. They look quicker, sharper, more prepared for the future. Historians still argue exactly how reptiles branch into the many lineages that later dominate Earth. Early evolutionary relationships remain complicated because the fossil record often resembles nature scattering puzzle pieces across several continents and then burying half of them out of spite. You continue walking beneath tall conifer-like trees swaying in warm wind. Seed plants become increasingly important now. Unlike earlier spore-based plants, seeds protect developing embryos and survive harsher conditions. Forests gradually shift composition as ancient swamp ecosystems decline. The land itself feels more varied too. Mountain ranges rise where continents collide. Vast deserts stretch across Pangaea's interior because moisture from surrounding oceans struggles to reach the center of the enormous supercontinent. Seasonal extremes intensify. Summers scorch. Winters cool sharply inland. Pangaea basically turns huge portions of Earth into the world's largest inconvenient road trip. A quirky fringe tidbit from this era involves fossilized footprints found in ancient dune deposits. Some trackways preserve tiny details of skin texture and movement patterns, allowing scientists to estimate how early reptiles walked across prehistoric sand hundreds of millions of years ago. Entire vanished afternoons survive in stone because one creature wandered through mud at exactly the right moment. You climb a rocky ridge overlooking dry valleys dotted with hardy vegetation. Conifers rise among seed ferns while rivers snake across dusty plains below. Insects still thrive, though atmospheric oxygen gradually declines from carboniferous peaks, limiting some of the extreme gigantism seen earlier. So yes, the era of dragonflies the size of hawks slowly begins ending. Humanity collectively breathes a small sigh of relief several 100 million years later. You hear rustling nearby. A reptile-like creature emerges cautiously from beneath low vegetation. Its body remains somewhat sprawling, but it moves with clear purpose across dry ground. Tough scales protect it from dehydration. It no longer needs to stay close to water the way amphibians do. This evolutionary freedom changes everything. Animals can now spread into arid regions previously inaccessible to vertebrate life. Deserts, uplands, and seasonal environments suddenly become available habitats. Historians still argue whether some early reptile groups are direct ancestors of later mammals, reptiles, or entirely separate lineages. One major branch called synapsids begins evolving features that eventually lead toward mammals, though at this stage they still look distinctly reptilian to modern eyes. And some of them look wonderfully bizarre. You approach a sunlit clearing where sail-backed creatures bask near scattered rocks. These are early synapsids like Dimetrodon, among the most iconic animals of the Permian world. Despite often being mistaken for dinosaurs in toy stores everywhere, Dimetrodon actually predates dinosaurs by tens of millions of years. It also technically sits closer to mammals on the evolutionary tree than to dinosaurs. Which means somewhere, biology teachers are still correcting this misunderstanding with exhausted patience. The tall sail along its back likely helps regulate body temperature, warming quickly in sunlight or releasing excess heat later. Its jaws bristle with sharp, differentiated teeth, another hint of mammalian ancestry developing gradually over time. Predators become more efficient now. Ecosystems grow harsher and more competitive beneath the dry climates of Pangaea. You continue through scrubby woodland while warm wind carries dust across the landscape. Small reptilian herbivores nibble tough vegetation nearby. Insects buzz among seed ferns. Far overhead, the sky stretches clear blue without the constant humidity of carboniferous swamps. Earth feels older somehow, more mature. The lush, endless wetlands of earlier ages are fading into memory. Historians still argue how rapidly Pangaea assembles and how strongly its formation influences climate change during the Permian. Some scientists emphasize volcanic activity and atmospheric chemistry. Others focus on continental positioning and ocean circulation disruptions. Either way, the world becomes increasingly extreme. You stop beside a dried riverbed cracked beneath the sun. Seasonal droughts shape ecosystems here. Survival depends on conserving water, tolerating heat, and reproducing efficiently away from shrinking wetlands. Traits reptiles handle far better than amphibians. And as evening settles across the supercontinent, you can almost sense the balance of power shifting. The age of sprawling swamp creatures is fading. A tougher world is arriving now. One built for scales, claws, sharp teeth, and survival beneath harsh skies. The deserts stretch forever. You stand deep within the interior of Pangaea, where dry winds sweep across red stone valleys beneath a blazing sun. Mountain ranges rise blue-gray in the distance. Sparse forests cling to riverbanks, while enormous dune fields ripple toward the horizon like frozen oceans of sand. The lush carboniferous swamps are mostly gone now, replaced by a harsher world shaped by heat, drought, and brutal seasonal extremes. And somehow, life absolutely thrives in it. Welcome to the Permian period, roughly 299 to 252 million years ago, where strange reptilian creatures and mammal-like synapsids dominate the land long before the first true dinosaurs ever appear. Honestly, if someone told you this world existed in a fantasy novel, you would probably accuse the author of making up too many sail-backed lizards. The mainstream historical fact here is that the Permian sees the rise of diverse synapsids and reptiles across the supercontinent Pangaea. Synapsids, including famous animals like Dimetrodon and later therapsids, represent evolutionary relatives of mammals rather than dinosaurs. You walk across cracked earth while heat shimmers above the ground. Nearby, a herd of bulky herbivorous synapsids grazes on tough seed ferns and conifer branches. Their legs still sprawl somewhat outward, but some species already show more upright posture and advanced jaw structures, hinting at future mammalian evolution. One creature lifts its head towards you briefly, nostrils flaring in the dry air. There is intelligence in the movement. Not human intelligence, obviously. More the cautious awareness of an animal very familiar with the concept of being eaten. Predators patrol these lands constantly. You crest a ridge overlooking a broad floodplain, where a massive carnivorous synapsid prowls between scattered trees. Its differentiated teeth slash through flesh more efficiently than the simpler jaws of earlier reptiles. Powerful muscles ripple beneath scaly skin, while the famous sail on its back catches the afternoon light. Despite all appearances, this creature is not a dinosaur. Dinosaurs still have not shown up yet. They are basically late to Earth's evolutionary party, while these strange mammal relatives run the place. Historians still argue exactly why synapsids become so successful during the Permian. Some researchers point toward metabolic advantages, improved feeding efficiency, and better adaptation to dry climates. Others emphasize environmental instability, selecting for versatile survivors. Either way, these animals dominate much of terrestrial life. A quirky fringe tidbit from this era involves fossilized burrows discovered in South Africa and elsewhere. Some Permian animals appear to shelter underground during harsh weather conditions, and a few fossils even preserve curled-up bodies inside ancient burrows. Which means the instinct to hide indoors when conditions become unbearable predates humanity by a very impressive margin. You continue across dry woodland where early therapsids moved through patches of shade beneath tall conifers. These later synapsids look increasingly mammal-like compared to earlier forms. Some possess more upright legs, more complex teeth, and possibly even higher metabolic rates. A few may already have whisker-like sensory hairs. Tiny hints of mammals quietly emerge in a world still ruled by reptilian giants. The climate feels relentless now. Days scorch beneath intense sunlight, while nights cool rapidly across the desert interior. Seasonal monsoons flood some regions temporarily before disappearing again. Pangaea's enormous size creates dramatic weather patterns unlike anything modern Earth experiences, and the skies often glow hazy red with dust. You kneel beside a shallow watering hole crowded with life. Amphibians linger near the muddy edges where moisture remains reliable. Insects buzz among scrubby plants. Reptiles bask on warm stones while larger predators patrol nearby. Everything here feels tougher than earlier ecosystems. More armored, more competitive, more prepared to survive scarcity. Historians still argue whether some Permian synapsids possess partially warm-blooded metabolisms. Bone structure and growth patterns suggest certain groups may maintain more stable internal temperatures than traditional cold-blooded reptiles. The line between reptile and mammal remains wonderfully blurry here. Evolution rarely bothers with neat categories. You climb higher into rocky hills where sparse vegetation clings to dry slopes. Far below, rivers carve winding green corridors through otherwise harsh terrain. Life concentrates heavily around water sources now, and predators know it. A large Gorgonopsian emerges from the brush ahead, one of the apex hunters of the late Permian world. Its long saber-like teeth gleam pale against dark gums. Unlike earlier sprawling predators, it moves with unsettling confidence and efficiency. There is something strangely familiar about its posture. A glimpse of future mammalian predators hidden inside a deeply ancient body. Honestly, if a tiger and a reptile collaborated on terrible decisions, this might be the result. A warm wind sweeps across the landscape, carrying the smell of dust, resin, and distant rainstorms. Thunderheads build slowly over far mountains while the fading sun paints the desert gold and crimson. Earth feels ancient now in a fully recognizable way. There are forests, predators, complex food webs, animals adapted for deserts, rivers, uplands, and plains. Yet beneath all this thriving diversity, danger quietly builds. Massive volcanic systems begin stirring deep within the crust. Atmospheric carbon dioxide levels fluctuate. Oceans experience chemical stress. Climate instability grows more severe toward the end of the Permian. Historians still argue exactly which factors matter most. Volcanoes, methane release, ocean anoxia, global warming, acid rain, declining oxygen, perhaps all of them together. The planet is approaching catastrophe. You stand beneath darkening skies while herds of herbivorous synapsids move cautiously across the floodplain below. Predators lurk at the edges of fading light. Dust swirls across ancient Pangaea beneath an uneasy horizon. The world appears strong, dominant, untouchable. But Earth has ended thriving ecosystems before, and it is preparing to do it again on a scale almost impossible to imagine. At first, the world simply grows hotter. You notice it in the rivers shrinking earlier each season, in forests struggling beneath relentless drought, in the uneasy silence spreading through ecosystems that once felt stable. The skies over Pangaea turn hazier year after year, stained by volcanic gases drifting through the atmosphere. Sunsets glow blood red through thickening clouds while distant horizons flicker constantly with eruptions. Something enormous is happening beneath the planet's crust, and life has absolutely no idea what is coming. You stand near the end of the Permian period, roughly 252 million years ago, during the greatest mass extinction Earth has ever experienced. Entire ecosystems teeter on collapse. The continents still form the vast supercontinent Pangaea, but now its interior bakes beneath extreme heat, while catastrophic volcanic eruptions tear open the land in what will later be called the Siberian Traps. The name sounds oddly metal for something capable of nearly ending complex life. The mainstream historical fact here is staggering. The Permian Triassic extinction event wipes out around 90% of marine species and roughly 70% of terrestrial vertebrate species. It is often called the Great Dying because no other extinction event in Earth's history approaches its scale. You walk across a dry floodplain where ash drifts softly from the sky like grey snow. Forests stand dead in many regions, their trunks blackened beneath acidic rain. Rivers run sluggish and warm. The air itself feels wrong somehow, heavy with volcanic gases and lacking freshness. Far to the north, unimaginable eruptions continue pouring lava across millions of square kilometers. The Siberian Traps release colossal amounts of carbon dioxide, sulfur dioxide, and other gases into the atmosphere over immense spans of time. Earth's climate begins spiraling out of control. Temperatures rise dramatically. Oceans warm and lose oxygen. Acid rain lashes the continents. Methane may erupt from ocean sediments, accelerating greenhouse warming even further. Honestly, the planet starts behaving like it accidentally clicked every disaster setting at once. Historians still argue exactly which mechanisms drive the extinction most severely. Some researchers emphasize volcanic greenhouse warming. Others focus on ocean acidification, toxic hydrogen sulfide release, collapsing food chains, or declining atmospheric oxygen levels. Most likely, several overlapping catastrophes combine into one prolonged biological nightmare. You continue through a dying forest where insects buzz weakly among brittle vegetation. Animal tracks grow scarce. A herd of exhausted herbivorous synapsids picks through sparse plant growth near a muddy riverbank. Their ribs show beneath stretched skin. Predators appear thinner too. Even the survivors look tired. A quirky fringe tidbit from this era involves fossil evidence suggesting fungal blooms spread widely after the extinction, feeding on vast amounts of dead organic material. Some scientists call it the fungal spike. For a brief geological moment, Earth may literally become a planet of decay, which is a deeply unpleasant mental image right before bedtime. The oceans suffer even worse. You stand now beside a coastline where dark waves roll beneath a sickly sky. The water smells sulfurous and stagnant. Coral reefs collapse. Trilobites, survivors of hundreds of millions of years, finally disappear entirely. Countless marine species vanish from existence. Some parts of the ocean may become nearly uninhabitable, depleted of oxygen and filled with toxic chemicals. Imagine entire seas forgetting how to support life. You watch dead fish wash ashore beside black volcanic sand while storms gather overhead. Lightning flashes through thick clouds carrying acidic rain inland. Forest fires rage across drought-stricken regions, filling the atmosphere with smoke. Earth itself seems feverish. Historians still argue whether atmospheric oxygen levels fall low enough during the late Permian to make breathing difficult for large animals. Some evidence suggests oxygen concentrations may decline significantly, placing additional stress on already struggling ecosystems. Even simply existing becomes exhausting. You climb a ridge overlooking a valley, littered with fallen trees. Silence hangs over the landscape now. The buzzing insect chorus of earlier eras fades. Large animal populations crash across entire continents. Ecosystems unravel piece by piece. And yet, some creatures survive. Small adaptable species shelter in burrows, cling to wetlands, or endure harsh conditions long enough to outlast the catastrophe. Among them are certain therapsids, distant relatives of future mammals. Tiny survivors carrying entire evolutionary futures on their backs. A warm wind blows ash across the ground, while the sun glows dim orange through volcanic haze. Rivers flood unpredictably now due to climate chaos. Deserts spread farther. Seasonal extremes intensify. Food webs collapse faster than they can recover. The Great Dying unfolds over thousands of years, perhaps longer. Not one sudden apocalypse. A long unraveling, which somehow feels even more haunting. You pause beside the skeleton of a massive synapsid, half buried in dust. Once these animals dominate Pangaea. Now many lineages vanish forever. Entire branches of evolution disappear without descendants. Predators, herbivores, reef builders, ancient survivors from earlier worlds. Gone. Historians still argue whether the extinction nearly sterilizes Earth completely or whether some ecosystems remain surprisingly resilient. Fossil evidence suggests certain microbial communities and hardy species recover relatively quickly in isolated regions. Life bends frighteningly close to collapse, but it does not fully break. You stare across the devastated landscape while thunder rolls through ash-dark skies. Far away, volcanic eruptions continue staining the horizon red. The forests are quieter now, the rivers emptier, the oceans darker. The Permian world is ending. Not with one impact or single explosion, but through a slow planetary poisoning that rewrites the rules of survival itself. And when the catastrophe finally begins easing, the Earth left behind will feel lonely, damaged, and strangely unfamiliar. A wounded world waiting for new rulers. The silence after catastrophe feels almost unreal. You walk across a landscape that once supported sprawling forests, roaring rivers, and thriving ecosystems. Now much of it lies barren beneath pale skies streaked with volcanic haze. Dead tree trunks stand like blackened pillars across empty floodplains. Rivers cut through dusty valleys, carrying ash and sediment into sluggish seas. Even the wind sounds quieter somehow, as though Earth itself is exhausted after surviving the Great Dying. And honestly, fair enough. Nearly everything is gone. The early Triassic world, beginning around 252 million years ago, feels broken in ways difficult to fully imagine. Ecosystems do not simply bounce back after the Permian extinction. Recovery takes millions upon millions of years. Entire ecological roles vanish. Food chains collapse. Biodiversity remains astonishingly low compared to earlier ages. The mainstream historical fact here is that recovery from the Permian-Triassic extinction is painfully slow. Fossil evidence suggests Earth's ecosystems remain unstable for millions of years afterward, with repeated environmental crises disrupting the rebuilding process. You stand beside a shallow river, winding through dry red plains beneath a hot sun. The climate remains harsh. Temperatures stay elevated from lingering greenhouse conditions, while oxygen levels remain lower than modern Earth. Large regions of Pangaea continue suffering from intense heat and seasonal drought. Life survives, but survival looks difficult. A few hardy plants spread across the landscape, mostly drought-tolerant species adapted to unstable conditions. Forests begin returning in patches, though many regions remain sparse and scrubby compared to the lush Carboniferous worlds long gone. You kneel beside muddy tracks pressed into drying sediment. Small reptilian creatures passed through here recently, moving cautiously between water sources. Many surviving animals are relatively small, opportunistic, and adaptable. The age of giant dominant ecosystems is temporarily over. Historians still argue whether recurring volcanic activity and climate instability repeatedly interrupt recovery during the early Triassic. Some evidence points toward continued carbon dioxide spikes, ocean anoxia, and warming events that slow ecosystem rebuilding for millions of years. Earth keeps reopening the wound before it fully heals. A quirky fringe tidbit from this era involves so-called disaster taxa, organisms that spread rapidly after mass extinctions because they tolerate harsh, unstable environments better than specialized species. One famous example is Lystrosaurus, a sturdy herbivorous therapsid that becomes incredibly widespread after the Permian extinction. Imagine surviving the worst extinction in history simply by being adaptable, compact, and willing to eat almost anything. Basically the evolutionary equivalent of owning sensible hiking boots and canned food. You spot a herd of Lystrosaurus now near the riverbank. Their barrel-shaped bodies shuffle through dusty vegetation, while tusk-like teeth protrude from blunt snouts. They are not graceful animals. They resemble determined survival potatoes, but they endure. And right now, endurance matters more than elegance. The skies above Pangaea shimmer with heat haze while distant storms build over far mountains. Seasonal monsoons still lash some coastal regions, but much of the supercontinent interior remains dry and extreme. Vast deserts stretch across enormous distances beneath unforgiving sunlight. You continue walking through rocky uplands where strange reptilian survivors bask on warm stone. Archosaurs begin appearing more prominently now, an important group that will later include crocodiles, pterosaurs, and dinosaurs. At this stage, they remain relatively modest players in recovering ecosystems. Dinosaurs still have not taken over yet. In fact, if you wandered through the early Triassic expecting towering Jurassic giants, you would mostly encounter exhausted ecosystems and tough little survivors trying not to die. Historians still argue exactly why archosaurs eventually become dominant over other reptile groups. Some researchers emphasize efficient breathing systems and upright posture. Others point toward climate adaptability or simple evolutionary luck following repeated extinctions. Luck honestly deserves more credit in natural history. You climb a ridge overlooking a broad valley where sparse conifer forests spread beside winding rivers. Insects buzz through the warm air again. Amphibians lurk near shrinking pools. Small reptiles dart between rocks. Life slowly reclaims the land. The oceans recover too, though unevenly. Coral reefs remain rare for long stretches. Marine ecosystems rebuild cautiously, with new groups filling ecological gaps left empty by extinct species. Fish diversify again. Marine reptiles begin evolving from terrestrial ancestors returning to the sea. Earth refuses to stay empty forever. You pause beside a shallow lake, glowing orange beneath sunset. Nearby, a slender reptilian predator moves silently through the brush with legs positioned more directly beneath its body than the sprawling creatures of earlier eras. A more efficient posture, a more mobile design. Tiny hints of future dominance quietly emerge. The atmosphere feels different from older worlds too. The haze of volcanic catastrophe slowly fades over millions of years. Oxygen levels recover gradually. Temperatures stabilize somewhat, though the climate remains warmer than today. The world is healing, slowly, unevenly, but healing nonetheless. Historians still argue whether ecosystems after mass extinctions become more innovative because ecological niches suddenly stand empty. With so many dominant groups gone, surviving organisms may diversify rapidly into newly available roles. Evolution hates a vacancy. You continue along the lakeshore while twilight settles across recovering Pangaea. Frog-like amphibians croak softly from reeds. Small reptiles rustle through dry vegetation. Overhead, unfamiliar stars shine through clearer skies than those of the volcanic Permian nightmare. For the first time since the Great Dying, the planet feels hopeful again. Not peaceful exactly, more like resilient. Life bends nearly to the breaking point, then quietly begins rebuilding from the ruins. And somewhere out there among the archosaurs moving through these recovering ecosystems are small creatures that will eventually reshape Earth completely. At the moment, though, they are still just background characters in a wounded world, learning how to breathe again. The world grows crowded again. Not with the giant swamp insects of the Carboniferous or the sail-backed hunters of the Permian, but with new reptilian lineages spreading across recovering ecosystems. Rivers flow through green valleys once more. Forests thicken across parts of Pangaea. Insects hum through warm evening air, while unfamiliar predators stalk the edges of lakes and floodplains. Earth is alive again, but it still carries scars. You walk through the Middle Triassic world, roughly 245 to 235 million years ago, where ecosystems rebuild into something entirely new after the devastation of the Great Dying. The climate remains warm overall, with strong seasonal monsoons along coastal regions and vast dry interiors farther inland. Pangaea still dominates the globe, stretching almost pole to pole like an enormous cracked shield. And across this recovering supercontinent, strange survivors experiment with new forms. The mainstream historical fact here is that the Triassic period becomes a time of evolutionary recovery and diversification. Archosaurs spread widely, eventually giving rise to crocodilian relatives, pterosaurs, and the first dinosaurs, while mammal ancestors persist in smaller ecological roles. You move through a dense conifer forest where broad-leaved cycads grow beneath towering trees. Ferns carpet the forest floor beside streams winding through red soil. The air smells warm and resinous beneath soft morning fog. A reptilian predator bursts briefly through the undergrowth ahead before disappearing again. Its legs stand more upright beneath the body compared to older sprawling reptiles. Movement looks faster now, more efficient. Archosaurs are becoming increasingly successful. Historians still argue whether archosaurs gain dominance because of superior lung systems that help them thrive in low oxygen conditions. Some researchers believe airflow patterns inside their respiratory systems allow more efficient breathing than many competing groups. Basically, better breathing quietly becomes one of evolution's greatest competitive advantages. You continue deeper into the forest while strange creatures move through the shadows around you. Some resemble crocodiles on long legs, adapted for running rather than lurking in rivers. Others climb trees or patrol shorelines. Early pterosaurs begin appearing too, small flying reptiles flapping awkwardly above the canopy. The skies themselves are changing now. For hundreds of millions of years, insects rule the air alone. Suddenly, vertebrates join them. And honestly, the first pterosaurs look like nature assembled them from leftover spare parts at high speed. A quirky fringe tidbit from this era involves fossilized footprints discovered long before matching skeletons are found. Some Triassic trackways hint at mysterious animals decades before paleontologists know exactly what made them. Entire prehistoric creatures essentially announce themselves with footprints first, like ancient celebrity teasers. You kneel beside one such trackway pressed into hardened mud. Narrow footprints move in a surprisingly upright pattern across the ancient floodplain. Small, fast, balanced, different. Nearby, tiny mammal relatives scurry through leaf litter beneath the feet of larger reptiles. These early cynodonts possess increasingly mammal-like features. differentiated teeth, possible fur, and perhaps even warm-blooded metabolisms. But for now, they mostly survive in the shadows while larger reptiles dominate open ecosystems. Future mammals are basically tiny, anxious night creatures at this stage, which feels strangely relatable. The climate grows increasingly unstable again in some regions. Seasonal floods alternate with severe droughts across Pangaea's interior. Volcanoes rumble occasionally along tectonic boundaries while shifting coastlines reshape habitats. Yet biodiversity continues increasing despite the instability. You emerge from the forest onto a broad floodplain, alive with movement. Herds of herbivorous reptiles graze among cycads and ferns, while predators patrol nearby riverbanks. Fish dart through shallow waters beneath dragonflies gliding overhead. The world finally feels abundant again after the bleak emptiness following the Permian extinction. Historians still argue how quickly the first true dinosaurs evolve during the late Middle to early late Triassic. Fossil evidence suggests they begin as relatively small animals among many competing reptile groups rather than immediate rulers of Earth. Dinosaurs actually start humbly. No thunderous dominance, no dramatic takeover montage. Just small bipedal reptiles trying to survive among crocodile relatives, giant amphibians, and countless other competitors. You spot one now near the edge of the floodplain. A slender animal no taller than a large dog darts between patches of vegetation. Its hind legs move beneath the body with striking efficiency. The tail balances its motion as it pauses alertly, scanning the environment. One of the earliest dinosaurs, and almost nobody alive at the time would guess what its descendants eventually become. The creature disappears quickly into the brush while larger archosaurs continue dominating the area around you. Dinosaurs remain minor players for now. Evolution has not yet handed them the spotlight. A warm wind sweeps across the floodplain, carrying the smell of wet soil and distant rain. Thunderheads gather beyond far hills while evening sunlight paints the forest's gold. You realize something quietly profound standing here. The Earth before dinosaurs does not end with one sudden transition. There is no dramatic moment where ancient worlds stop and dinosaur worlds begin. Instead, ecosystems shift gradually. Survivors adapt. New groups emerge quietly among older ones. Life rebuilds itself layer by layer after catastrophe. And now, at the edge of the late Triassic, dinosaurs wait patiently in the background of their own future empire. Small, quick, almost unnoticed, but not for much longer. The night air feels warm and still across the Triassic floodplain. You stand beneath tall conifers while insects hum softly through the darkness and distant thunder rolls across the horizon. Somewhere nearby, small early dinosaurs move quietly between shadows, lean bodies balanced on powerful hind legs. They are not rulers yet, not even close. Larger reptilian predators still dominate many ecosystems. Crocodile relatives stalk rivers. Massive amphibians linger in wetlands. Mammal ancestors remain hidden in burrows and undergrowth. And yet, the balance is beginning to tilt. Slowly, almost invisibly. You walk along the edge of a shallow lake reflecting moonlight beneath the enormous shape of Pangaea's skies. The continents remain joined together, though deep cracks now spread across parts of the supercontinent as tectonic forces prepare to pull it apart. Volcanoes rumble in the distance. Forests stretch across broad valleys. Life thrives again after the long shadow of the Great Dying. Earth has rebuilt itself once more. The mainstream historical fact here is that by the late Triassic, around 230 to 201 million years ago, the first true dinosaurs diversify alongside many competing reptile groups. They remain relatively modest at first, but evolutionary pressures and future extinctions soon allow them to dominate much of the planet. You crouch beside fresh tracks pressed into damp mud near the shoreline. 3 slender toes, upright stride, efficient movement. A dinosaur passed through here recently. Not the giant thunderous creatures people usually imagine. No towering tyrants yet. These early dinosaurs are smaller, quicker, and surprisingly delicate looking compared to later descendants. Some hunt insects or small animals. Others graze on vegetation in scattered herds. Tiny beginnings for future giants. Historians still argue exactly why dinosaurs eventually outcompete many rival groups. Some scientists point toward efficient locomotion, rapid growth, advanced respiratory systems, or sheer adaptability during periods of environmental stress. Others think luck and extinction timing play enormous roles. Evolution often resembles survival, mixed with suspiciously convenient timing. You continue through the forest while early pterosaurs flap overhead beneath starlit skies. Their wings rustle softly through humid air as they hunt insects near the canopy. Nearby, small mammal relatives emerge cautiously from burrows to forage at night, avoiding larger daytime predators. Future mammals still survive mostly as nervous little side characters. If Earth history were a movie, mammals at this stage would absolutely be listed somewhere deep in the credits. A quirky fringe tidbit from this era involves fossilized sleeping groups of ancient reptiles found curled together in burrow systems. Some researchers suggest social behavior and parental care may already exist in certain Triassic species, which means even before dinosaurs fully rise, prehistoric creatures may already cuddle for warmth and safety during cold nights. That image feels strangely comforting after 4 billion years of planetary chaos. The climate remains unstable in places. Volcanic activity increases as Pangaea slowly begins fracturing apart. Rifting continents create enormous lava flows and shifting environments. Carbon dioxide levels fluctuate again. Ecosystems face repeated stress, and another extinction approaches. Not as catastrophic as the Great Dying, but severe enough to eliminate many competing reptile groups near the end of the Triassic. Dinosaurs survive relatively well through the transition. Then they expand rapidly afterward. You stand at dawn overlooking a broad valley, where mist curls between conifer forests and winding rivers. Early dinosaurs move cautiously through the undergrowth, while larger archosaurs patrol open ground nearby. For one quiet moment, the future hangs perfectly balanced. The Earth before dinosaurs still exists around you. The old reptilian dynasties remain powerful. The mammal ancestors still hide in shadow. The great supercontinent still holds together beneath your feet. But change is coming again, as it always does on this restless planet. Historians still argue whether dinosaurs are already destined for dominance at this point, or whether they simply benefit from surviving environmental disasters that wipe out competitors. Perhaps in another timeline, crocodile relatives inherit the world entirely, while dinosaurs remain obscure, little hunters lost to history. Earth could have turned out very differently. You walk slowly through the awakening forest, while golden sunlight spills across ancient leaves. The world feels alive in ways impossible during the barren volcanic chaos of Earth's youth. Oceans shimmer beyond distant hills. Forests breathe beneath warm winds. Animals call through the trees. From molten beginnings beneath toxic skies to microbial oceans, frozen worlds, giant insects, sail-backed predators, and now the first dinosaurs quietly stepping into the future. The journey has been impossibly long and strangely beautiful. You pause beside the lakeshore one final time while soft ripples spread across the water. Above you, Stars fade slowly into dawn. The earth keeps turning, just as it always has for billions of years, reshaping itself endlessly through fire, ice, catastrophe, and renewal. And now the pacing softens. The forests grow quieter around you. The wind eases through the branches with a low, gentle hush, almost like distant waves folding against a quiet shore. Somewhere in the distance, an unseen animal calls once, then fades back into stillness. The warm air carries the scent of damp soil, pine resin, and rain waiting far away beyond the hills. You sit beside the ancient water and simply watch the planet breathe. No cities glow on the horizon. No engines hum. No voices interrupt the slow rhythm of the natural world. Only the enormous calm of deep time, stretching endlessly backward and forward beyond your view. The stars overhead dim one by one as morning slowly arrives across prehistoric Earth. Tiny insects drift above the reeds. Mist curls low over the water. Somewhere in the forest, one of those small early dinosaurs moves softly through the undergrowth, unaware that its descendants will one day rule the world for millions of years. But that story belongs to another night. For now, the earth before dinosaurs settles gently around you, ancient and patient beneath the brightening sky. And as the sunlight slowly warms the still water beside you, you let the vastness of it all drift quietly through your mind, before finally fading into sleep.